I will start lecturing content here in a moment, but so what else was I going to say about what's required? Oh, the schedule. The schedule is I will be here every day I can be. This week that means today, Wednesday, and Thursday. I'll be in Delaware on Friday. So, but you will still have class, because what will happen? Brian or the other student will come in and they'll figure out how to use this DVD player up here, and you can watch the beginning of the 337 lectures. 337 is really welding. It starts out with how things bond and why welding is important and things like that. It was the original 6-unit welding course. And there's 25 of those lectures, and it goes through cold welding, adhesive bonding, soldering, brazing, which is electronics manufacture. You said you were in a consulting engineering firm. What type of consulting?
Transportation industries, like automotive, defense, commercial.
Okay, so, because I'm going to try to give a few examples more towards you, because supposedly they're going to maybe use this again like they used to, not for SDM, but it used to be kind of required, semi-required for LFM students, so far as that goes. But then LFM became almost totally a management program and almost no engineering content, and essentially got dropped. So the schedule is you come every morning. We actually will probably finish I may be gone every day next week. I may be here Monday and Tuesday. I don't know, but I know I'm gone Wednesday, Thursday, and Friday next week. But you can just plan to be here every day, okay? Now, it's likely I might finish up before July 4th in terms of live lectures, in which case, if you want, you don't have to come in early. If you can find another time during the day for groups of you to watch it, and some people watch it at home. One student I know took the course once, and he told me he watched it every night while he's fixing dinner, okay? So how can you watch the course while you're fixing dinner? Well, first of all, this is not your typical MIT course. I solved one differential equation just to prove I'm an MIT professor, okay? But in general, we're not heavy on the math. 2N students will get all the math you want over the next few weeks, and maybe a little more. It's more talking about physical principles, things that over the years I've learned are useful in solving engineering problems of a wide range of industries, from electronics manufacture through shipbuilding. I sometimes used to say from chips to ships, okay? So we'll try to bring in some of those examples, and I'll probably try to do a little bit more of non-Navy things. The last couple of years I've done mostly Navy examples because that's who the audience was. Any questions? No questions? So you get to come, oh, I haven't told you what you have to do for the course. Somewhere in that handout, there is, the handout first is a list of comments. The second handout in here is an outline of the 6-unit course. And then somewhere in here, there's something called Chapter 16. It's actually about the 4th one in. This is an outline of that 6-unit course that I wrote about 1990, okay? You can forget reading all the rest of this if you just read this little chapter here. It's sort of my prose content of everything you need to know about welding and joining. And at the back of this, you have two things. MIT requires that I get something from you in order to give you an individual grade. In the back of this, there are 10 problems. And you can do the problem set, and that's your required work, or you can do a term paper. And the term paper should not take more than 10 hours total, study, research, writing. Shouldn't be more than 10 pages. You don't want to write that more than that, and I don't want to read more than that. You can do either one. If you do the homework, which has been the one of choice, I don't mind if you get together in groups and hand in a single homework. The record is 19 students turned in one homework. However, the requirement is that you actually get together and as a group discuss the problems. And I also will point out in there that the problems are, some of them are very open-ended. Some of them have too much information, some of them don't have enough information, so you have to make estimates of various things. So some of them are actually designed as real engineering problems where you don't have all the information. But I don't care, as long as you all get together, everyone, understands the problem. If everyone was doing each problem, all 10 problems alone, you'd come up with 10 different answers. That's fine. I don't know that there is a correct set of answers. I look them all over, okay, and I will see if you come up with a reasonable answer, and if it's reasonable, that's fine. That's really all you have to do for the course. Now you'll find some students found the rest of the readings valuable, some of them didn't. I think the readings are getting a little bit aged. I need to kind of get some newer references, but the principles are still the same. So there's another packet of similar size for this 12 units that I added on in 1999 or whatever on material selection and other things. So that's what you're required to do. And to a certain extent, 2/3 of this course, the welding point part this term, is self-paced. Although for the next 3 weeks, you should just plan on coming here every morning, and I'll either be here live or you can watch the video of me talking about welding. Okay? And after that, the last 15 or 20 hours, you can schedule that, watching those videos on your own. Okay? But hopefully the course is entertaining. It's most entertaining if you ask questions. Okay, so let's start, if there's no other questions, and talk a little bit about, well, actually, before I start that, were any of you MIT students before? None of you. Okay, so I have something for you. Although, I don't know if I have enough. I think I told Jerry to expect 15. I didn't get a good count. 3, 6, 7, 12. Looks like I got 16 here now. So here's a MIT faculty newsletter article that I wrote 2003 or 2004, based on about 30 years. I came here as a freshman in 1968 and have been here every year, about 3 since then. I worked 2 years at Buckland Steel, and in 1984 and 85 I worked for the U.S. Office of Naval Research in Tokyo, Japan for a year. But I've been here for, what's that make it out of, 38 years out of the last 41 or something like that. And when I wrote this article for the faculty newsletter about what makes MIT unique, I was actually writing it to try to make sure that Bob Brown, the former dean of engineering when I was department head, and then he became provost, didn't become MIT president. And fortunately he didn't. He went to Boston University, and when he left to go to Boston University, I sent him an email saying, hi. Okay, Bob Brown was a man of very, well, he was ethically challenged, I guess, is the best way for me to put it. But I actually wrote the article, and there's a quote in there from Bob Brown, that's the only thing you'll see, but it'll talk about what makes MIT unique, and sort of what the MIT experience is. When I wrote it, I found there was one faculty member in humanities who said he quit reading the faculty newsletter for the last 15 or 20 years because he found there was nothing in it. He decided that based on this article, he would start reading it again. I don't read it much myself. And then I got a lot of my old classmates in the living group I was in. They passed it around to a bunch of alumni. The alumni liked it. So I think you're all going to be going through a new experience here at MIT. MIT is, it's not unique among all universities, but it's different. The only one that I know that's similar to it, you'll see in there, is Caltech. We only admit one class of students, and that's scholars. We don't admit athletes, or you might know the 3 classes of students at Princeton and Harvard and Stanford will readily admit they admit scholars and athletes. And what's the 3rd class? Anybody know? Yes, exactly. Okay, but they call those legacy students. Okay, which means they're sons and daughters of wealthy alums. Okay, so yes, it's people with money. MIT only admits scholars. Nonetheless, until recently with the budget cutbacks this year, MIT used to be tied or just second or sometimes #1 with the Coast Guard Academy as having the most varsity NCAA sports. We had 41, and we dropped back to 34 because of the budget cuts this past year. But Coast Guard Academy and MIT were always around 40, 42, depending on how many teams they put out that each year. And these 2 schools had more athletic sports than any other college in the country. And people are somewhat surprised when I tell them that. And then I explain explained to them, MIT's emphasis on athletics is not winning, it's participation. Okay? To have as many students as possible participate. Whereas at other universities, anybody here from Ohio State? No? University of Florida? University of Michigan? I don't have any, there you go. You know what it's like, right? Football rules. Texas, how about Texas? Nobody from Texas? Anyway, there's a number of actually states where football runs the program. Other places it might be hockey, other places it might be basketball. But in any case, we actually have a football team. People are surprised. And I often point out we sometimes beat some good prep high schools. You know, but I think we're class 3, Division 3A or something. I mean, it's a division no one ever heard of. Anyway. Okay, let's get into technical things. And I guess I'll hand out this, which is the outline for the material selection part. So for this next 3 lectures, if you were to read one thing, and one thing only, there's 4 pages here, comes out of a National Research Council study called Materials Research to Meet 21st Century Defense Needs. And it's a panel of people, and I wrote Appendix C, and so I'm handing out Appendix C. Appendix C is basically an outline of the next 3 lectures. All I did was kind of write up what I've been talking to students about for years, as far as that goes. Now, so that's kind of the beginning of that. Let's talk a little bit about materials. And you're going to see that I tend to use, because some of my things come from various years. I use this thing because I can put pictures under here and put overheads under here, hopefully. But if I look at many people look at materials and say, well, I just need to know the composition of the material. Turns out that's not necessarily true. Here are 2 crystal structures, and it happens to be, both of them happen to be carbon. And you can tell it's carbon because the atoms are black. Okay? This is called graphite, and it has kind of a layered structure. Okay? This is called diamond cubic, and it actually has a cubic structure, which is this little white cell in here, and it's, if you know anything about crystal structures, it's got a face-centered lattice, which means it's got points at each corner and an atom right in the center of each face, and then it actually has a couple of other little atoms in there, hidden inside, four other atoms inside. But this is the crystal structure of graphite. This is the crystal structure of diamond. And because, even though it's the same atom, because it's different bonding, this has what we call sp2 bonding. And the atom in the center has 3 atoms around it. And essentially it has one up and above and below these different layers. But the strength of that bond is nowhere as strong as the bonds in the plane. And so you have sheets of atoms. And when we get to the welding part, I'll tell you about the history of the early Mercury flights and how they ran into problems with that when they first put their lubricants up in space. The first Mercury flights, the graphite lubricants turned to abrasives. And so some of the knobs and switches didn't work very well. Okay. Diamond cubic, on the other hand, has what we call sp3 hybridization, and each atom is surrounded by 3 others in a tetrahedron. Okay? A tetrahedron is like a 3-sided pyramid with a triangular base. Okay? That difference in bonding has tremendous differences in the properties of these. So the bonding in graphite is sp2, diamond is sp3. The crystal structures are different because they reflect the geometry of the bonding. The density is different. Whether they're transparent, diamonds are transparent to visible light or opaque. Actually, diamond is transparent further into the infrared than any other crystal we have. And so if you're really using fancy, really fancy, very long wavelength infrared, you sometimes have to use diamond windows on your detectors. Okay? Not because they're hard or because they're expensive, but because they're transparent, down to about 50 microns, and there's nothing else that goes below about 40 microns. Electrically, it's an insulator. Over here, it's a conductor. Thermal, it's isotropic and a very high thermal conductivity. Here, it's an anisotropic and somewhat moderate thermal conductor. Here, it's an abrasive. Here, it's a lubricant on Earth, but in space, it becomes an abrasive. Okay. Mechanical hardness, extremely hard, is the hardest material we know. This one is relatively soft. We use it as a lubricant. Abundance, rare, very abundant. Cost, very high, and low to high. And by low to high, this is a piece of anthracite coal, basically graphite. This is a piece of a carbon-carbon composite that was being developed to make a filter for chemical plants and other places, because carbon, graphite, has about the best chemical resistance of any material. Doesn't dissolve in any reasonable solvent or acid. It's resistant to all those things. So what they do is they take polyacrylonitrile, a certain polymer, which is a fiber. You can weave it like a mat. And you roll it up on a mandrel, and you stick it in a furnace at about 2,000 degrees centigrade, not Fahrenheit, and you burn off all the other stuff, and you leave behind what you can't see here, but a very porous mass, which makes an excellent filter, chemical filter. So if you're trying to recover catalyst from some chemical processing plant or something, and you're dealing with, let's say you're making Kevlar, and you're trying to, Kevlar is made in concentrated sulfuric acid. This will take the concentrated sulfuric acid without eating away the pores, because it's so chemically inert. So that's relatively expensive graphite, because it's got a very specific structure. Anybody know, the largest application I know of that I've ever seen for carbon-carbon composites is in the aircraft industry. Anybody know what it is? Honeywell, used to be Allied Signal in Indiana, makes this. Brakes for aircraft are carbon-carbon composites. And you go to the Honeywell facility in South Bend, Indiana, and they have furnaces about twice the size of this room, vacuum furnaces that go to 2,000 degrees centigrade, and they lay up these polymer sheets, and then they form them into brake pads, basically, and cook them at 2,000 degrees centigrade, because the carbon is very strong at high temperature and has good thermal conductivity, and so it makes a good brake. And you need good brakes on a big jumbo jet, okay, or other aircraft. And that's an interesting industry too, because that industry has gone to a situation where United or Delta, they don't own the brakes on the airplane. They lease the brakes. Honeywell owns the brakes. Anybody familiar with this? It's also in the commercial. They also do this now with the whole jet engine. So on the United fleet, United doesn't own the engines. Pratt & Whitney owns the engines, and Pratt & Whitney leases the engines to United now. It's called power by the hour. United wants to pay a certain amount per hour of operation of those engines, and they don't want to have to worry about whether an engine fails and it's going to cost to repair it. They want to know, they want to have a fixed cost, sort of like derivative swaps. Okay, they basically rent the engine by the hour from Pratt & Whitney. Honeywell leases the brakes to all the airline companies for a certain amount, probably per landing or whatever, and it means that if the mechanics determine the brakes need to be replaced, they don't worry about the cost, because Honeywell is going to eat the cost. But Honeywell has an incentive to try to make the brakes last as long as possible, because they're going to eat the cost every time a mechanic determines they need to be replaced. Same thing on power by the hour. If United's mechanics decide we want to take that engine out and put another one in, Pratt & Whitney's got to pay for it. So that it actually is a pretty good system. It actually produces the right incentives for both parties. The mechanics for the airlines don't have to worry about the cost. Some other company that's leasing the brakes or the engine have to worry about the cost, and they have the incentive to make those products last as long as possible, because they'll make the most profit on their lease, right? So that's a common thing. So we can just find out when the Air Force is going to go to power by the hour, right? Fat chance in general is going to. Anyway, well, just think you could start leasing ships from Korea, right? Okay, so the point of this overhead is that materials is more than just chemistry. Materials is also the structure of materials, and how things behave is very dependent on the crystalline structure or other type of structure of the material. Now, when I turned this in sort of into a management course once, I called this, brighten it up a little bit. When the LFM thing started, this actually came out of the Christian Science Monitor in 1987. At the Graduate School of Business, now a professor gets up and says, now I know you all want to make money, but today we're going to discuss making things, actual things. This is the production class, and the students in the back saying, things, I don't want to make things. The other one says, I want to make money. The third one says, listen, let's sue the business school. We can make some money that way. Okay? So, frankly, I used to be sorted down on business schools in my youth as not really teaching a whole lot. And maybe at some point, if you ask me the right questions, I'll tell you the story about the history of MIT going bankrupt in 1916 when they built these buildings, and how Harvard built their engineering school, and things like that. But then I started working with the LFM program. I had a little more respect for the management school. And now, as I look back at the financial crisis, I decided I was right in my youth. Now, this is sort of the history of materials over time, and it comes out of a book by a guy named Ashby. Mike Ashby just retired a year or so ago as a professor at Cambridge University, but he was a professor at Harvard about the time this book came out, about 1980 or so, on engineering materials. This is one. He also has a green version. It's engineering materials too. But it's a way to think about selection of materials. And he later came out with this handy-dandy book, an appendix, called Material Selection in Mechanical Design. Mike Ashby is a world-class material scientist and mechanical engineer, and he talks about function, shape. He's talking about structural materials, which is primarily what we're going to talk about. This little set used to cost about 10 years ago $300, but this one is copyrighted, this one is not. And we're going to show you what's in the appendix here. But Ashby came up with something that's now called Ashby diagrams for material selection. And in fact, you can now buy a $50,000 computer program that helps you select materials. And this is in the beginning of Ashby's $300 book, where he looks at materials through the ages. This is sort of a nonlinear scale: 10,000 BC, 5,000 BC, 0 BC, 1,000, 1,500, 1,800. You can see that's not exactly linear in time. Relative importance, and back in 10,000 BC, people had gold. Later they had copper. They didn't have gold. They didn't only had gold as metal originally. Anybody know why? It's going to be part of a little later in today's lecture. Gold is the only material that people would find in its metallic state in 10,000 BC. Now, there was some metallic copper, but only in certain parts of the world. Wood, skins, fibers, stone, flint. And so he breaks it up into metals, polymers, composites, and ceramics. These are structural materials. Material scientists like this department used to organize itself around metals, plastics, ceramics, and electronic materials. Okay? But electronic materials are not a structural material. They're a functional material. Okay? So, and this is kind of how materials came about. This should be in the handout that you get later. Another thing, what I didn't say, and in fact, you're the only person with a computer. Okay? So I'll pay you a $500 bounty on your notes. Okay? Because this all goes into my website, the videos and everything. And if you want to take the notes, I usually look for whichever students have computers at first day. If you want to take the notes, the outline, it's on the website for the lecture. So if you want to sell me your notes, I'll buy them for $5,000. Not $5,000, $500, okay? That's the typical price. So if you don't want to do it, if you can convince someone else to bring a computer, but that's the standard price I've been paying for a few years. And they will go on, you know, onto the website. So you guys don't have to take notes, okay? And the people who watch my course by video anywhere in the world, they don't even have to take notes. The notes are already taken for them, okay? So, trying to make this course as easy as possible for people. Remember, when I first started teaching, it was an all-volunteer course. No one was required to take it. Now you guys are required to take it. That's why you're all here at 7:30. That's not really true. I used to get up here at 7:30 in the morning, even when it wasn't required. But the point is, well, actually, the point is, I didn't tell you, there's only one course, one grade, actually 2 grades. I used to give out incompletes, and they told me I can't do that. So there's really 3 grades I've given. Most people get 1 grade. I won't tell you what it is. And then I used to give out incompletes, and they said you can't do that because someone hadn't finished the problem set or their term paper. And they say I have to give Fs to anyone who hasn't completed things, and then the student has to deal with that and get it changed. Okay, but just so you know, this is a course that it started out no one was required to take it, and so the philosophy was just come to class and let's try to learn some things. Okay, we're not here to test you. I do have to require, the institute requires, the rules require that I get something from you to base your grade on. So I have to have that problem set, or I have to have that term paper. Beyond that, you don't have to read anything, there's no quiz, so just come and pay attention, okay? So anyway, this is kind of through the ages. Ashby wrote this about 1980 right in here, and he was projecting that metals were going to decrease in intensity and in importance. Polymers will become more important, and they do. Composites were going to become much more important from 1980, and ceramics and glasses. Now, those predictions have not really proven true. Metals are still about as important as they used to be as a structural material. Polymers have increased. Composites have not grown anywhere near the rate people were predicting. I used to say composites were the materials the future always were and always would be. And then you got straw back here is, you know, Pharaoh took away the straw from the Israelites to make their bricks. Okay? And ceramics and glasses he had increasing. But that was back in 1980 when everybody thought we were going to be flying around in ceramic turbine engines and things like that. Does anybody have an idea why? There's a reason for each one of these. Yeah?
Ceramics is a failure proportional to the size.
It's failure proportional to the size. It's a brittle material in layman's term, okay? And for brittle materials, the larger they get, the higher probability that you'll have a critical flaw in there. Volume of a critical flaw. With a larger volume, you get more critical flaw, larger critical flaws, and it's liable to fail. And so, if ceramics have excellent high temperature properties, the problem is they break. And in a jet engine, when something breaks, it's not always good. Okay? Composites. What's the problem with composites? Pardon me? Production? Yeah. This is a piece of the X32 Spaceplane. Guess what this cost? This was part of the liquid hydrogen tank. Weighed 4,000 pounds. Cost $50 million to build. You divide that out, $12,000 a pound, okay, for this material. So this is, we'll talk about that some more. But it's basically a commercial Kevlar honeycomb adhesively bonded to a graphite fiber reinforced composite that's all cooked in an autoclave and made into shapes, okay? But they built 2 of them, and $100 million as part of a $1.3 billion NASA program. And that wasn't the only reason, but they killed the program when that liquid hydrogen tank failed. And that's a piece of the failed tank that went into test in Huntsville, Alabama, in 5,000 gallons of liquid hydrogen, okay? And believe me, if you actually had a major failure on the pad of 5,000 gallons of liquid hydrogen, you would have a big explosion, okay? Anyway, so composites really are still facing the cost issue. And why has Boeing been delaying the 787 rollout, the Dreamliner? It's got more composites than ever before. The 777 was supposed to have lots of composites, but it turns out they cut back, and it turned out to be mostly aluminum in the end, not mostly composite. The Dreamliner, they had to make mostly composite, and that's delaying and driving up the cost. Plastics, what's the problem with plastics? Low temperature. They're only good at low temperature. You ever seen any 1,000-degree plastics? Yeah, it's called carbon. Okay, you burn off the plastic and leave carbon behind if there's no air around. If there's any air around, you leave air behind. Okay, carbon dioxide. Metals. Why are metals still the structural material choice? Well, not all metals are, and we'll talk about that. Okay, but a lot of them are. Over the years, there have been tremendous advances. For example, this is the firing temperature of jet engines, okay? Starting in 1950, remember it was after World War II. The jet engine was really sort of invented during World War II or a little bit before by this guy, what, Whittington or whatever in England. But it was really right after World War II, the V-2, was it V-2 bomber? The V-2 bomb that the Germans had at the end of World War II was really a jet engine, but it didn't have a long lifetime. It's sort of like a cruise missile. It only had to make it to the site and then blow up. Okay, so, but it started out where they used stainless steel or nickel nimonic 80, Martin Marietta 252, Unimet 500 Grenade, which is General Electric alloy. The temperature went up over time, and then they really didn't get to very, very much higher temperatures. These are operating temperatures in degrees C, okay, or degree F, sorry. Well, degree C on this axis, that's degrees F. And they went to single crystals and stuff, but the firing temperature went up, and the firing temperature in degrees C actually went above the melting point of the metal. So how was that? Well, it turns out that sometime around the 1970s, the Air Force programs, because they're sort of pushing the envelope, decided they could take some of the compressed air from the compressor in the engine and blow it through holes in the vane. So this is actually kind of a 1980s blade, technology blade. They're a lot fancier than this today, but it's hard for me to get copies of these things because every one gets serialized, and they have to account for every one because you don't want someone putting counterfeit parts into things, you know, the blade's no good, failed inspection. Because this thing, if it's good, it sells for $6,000. And there's about 100 of them in the set, so you're talking $500,000, $600,000 per stage, and you can have anywhere from 2 to 6 or 7 stages in the hot section of the engine. But basically they cast them, and this is an interesting casting technology, with holes in them, and turbulators, and you blow cooling air, 1,000-degree Fahrenheit cooling air comes out through here. They laser drill or EDM or electron beam drill holes at different angles. So the air comes out and creates a cooling boundary layer, 1,000-degree Fahrenheit boundary layer, because you've got 2,500 or 3,000-degree Fahrenheit combustion gases coming by this. The thing melts at around 2,400 F, but you're going to have gases at 2,500 to 3,000 surrounding it. So you got to cool it well, and you got to have the cooling air coming out to shield the surface. And in fact, that's a rotor part. This is a stator part, and this one actually has ceramic coating on it. Has even more cooling passages, and so you have cooling air coming through. That one's a single crystal. This one, I'm not sure if it's a single crystal or not. That came out of either a 747 type engine or a Pratt & Whitney that goes in a 747 or a 757 type of engine, Boeing jet type of engine. That's a stator. This has got a ceramic coating on there because the radiant heat flux actually is getting to be severe enough that you can damage the surface with ceramic coatings and stuff. And that's done by plasma spraying kind of coating technology. Now, to give you an idea, if your coatings aren't what they should be or you operate things improperly, this is a stator blade. It actually has some honeycomb here, and it actually has some rub marks because, actually this isn't stator, this is part of the rotor. That's got the rub marks. All right, I take it back, this is part of the stator. Because it's sitting like this, and the shaft is rotating this way, and it has these honeycombs that, as things grow with heat, they kind of grow into this. So you don't want a gas leakage through here. You actually have honeycombs that wear away. And you can actually feel the wear marks on that. That's a good blade, and you actually can see where they've coated it. This one's been repaired, and they put a coating in here. You can see the discoloration. This is one where the coating didn't work very well. This came out of an operating commercial jet, okay? And they were all like this. And if it had gone much longer, you would have lost the engine, okay? So, and it's all distorted and everything else. And, that's one of the reasons they knew it was a good time to take it out. Some of the engine operation was falling behind. But the materials didn't really advance as fast as they could in temperature, but there was this big change when they got to air cooling and started running 1,000-degree cooling air through the middle of these blades. And that's how all the engines, all the sophisticated engines run today. But they've kind of reached the limit of that, and they're still trying to push for things. This GTD 111 is sort of an interesting alloy. It says 1980 here. Yes, it was General Electric came out with it in 1980, and it really, in the composition, it didn't really meet the problems or requirements for a patent. And so General Electric didn't patent it, and other people over the next 15 to 20 years did start designing it into, because it was sort of a commercial alloy that was freely available to everyone. It wasn't patented. And people designed it into their systems. And then, in like 2001 or 2002, General Electric had filed for a patent back in the 1980s, and the patent office kept on rejecting it. And finally, they couldn't get one on the composition, but because of that first filing, they finally got a patent on the heat treatment of this alloy. So in early 2000s, all of a sudden, General Electric had a patent on this alloy 20 years after they had started using it, and about 15 years after other people started using it. So now all these other people who started using it were sort of in a tough spot, because General Electric said, oh, by the way, we just obtained a patent on the alloy you're using. We'd like royalties. So it got to be a real problem. Those are some of the types of things that happen from time to time. So if you can figure out some way to delay your patent, it's not the easiest thing to do. But okay, you can make out like a bandit. Okay. Now, it turns out, anybody know what the most commonly used metal in the world is, by far? Iron. Well, steel. In fact, the U.S. Army spent $50 million learning that. They did a study. Now, if they had come to me, I could have told them that. Okay? And I would have charged them only $48 million. Okay? But if you look at iron and steel world usage, and I think there's a paper, not in the set that I handed out to some of you, but in the other set, that I wrote around 1990 or so, called The Future of Metals. Because this was back when everybody said, oh, ceramics are going to take over metals in high temperature applications, and plastics are going to take over metals and this, that, and the other thing. And composites were going to take over metals, and everybody was maligning metals. And I wrote a paper saying, no, that's not true. Metals will still be around. Oh, and aluminum was going to take over steel and automobiles. Okay? They were predicting in 1990 that by 1995, 90% of all automobiles would be made out of aluminum rather than steel. And I used to go say, no, that's not true. Okay? So that's what a lot of the rest of the day is about. Why is steel the material of choice? 95 pounds out of every 100 pounds of metal made in the world is steel. Now, steel is not the most used structural material. Yeah.
It's abundant in strength and it's workable.
Exactly.
It's hard to work.
And
relatively.
The abundance comes low cost. Okay. So you got, if you throw low cost in there with your abundance, you got the top four: abundant, workable. It's also repairable. Okay. There are a number of things, and we're going to talk about what those various things are. But steel just has a special position compared to other things. In fact, if I want to think about selection of structural materials, now this was not showing up so well, but cost is number one. I don't care what anyone says. Cost is number one in structural materials. Now, if I'm talking a functional material like a platinum catalyst or a palladium catalyst for the catalytic converter of your car, that's a functional material. It's not structural. You're not building the whole car structurally out of platinum. But for structural materials by their very nature are used in large volumes. And that means the cost has to be reasonable. So I'm going to give you some rules of thumb for cost. Strength and fracture resistance. We're going to learn that metals are much better, much better than ceramics or plastics, most plastics. Some plastics are better than steels, okay? But availability, abundance, okay? So you've got that. Fabricability, okay? I think you said that. Recyclability and repairability. These are kind of the primary things. Why do we have to worry about recyclability? You know, the aluminum guys are very pleased with the fact that they recycle like 70% of all the aluminum nowadays. And they talk about, you know, you've seen the ads, haven't you? Or heard about aluminum as a recyclable material and people turning their cans. In fact, I have a guy with his grocery cart comes down my street every Monday morning before 7 o'clock, rooting through all people every other week when we put out our recyclables. And he's collecting those aluminum cans in my recycling and everyone else on the street. And there's a great story about this immigrant family in Los Angeles that put their son or their daughter through MIT by collecting tin cans, soda cans, and beer cans in Los Angeles. It's not easy to get $40,000 worth of beer cans, empty beer cans, okay? But his parents did it for 4 years. Well, that's not exactly true, but that's what the story would have you believe. In fact, I'm sure that their son or daughter was probably getting a 95% scholarship from MIT, and they probably only had to come up with $2,000 or $3,000 a year that they had to come up with. But they did it by collecting old beer cans. Okay? In terms of abundance, yeah, abundance, this is out of Ashby's book, out of this engineering materials book right here, in the very first chapter, and I guess I can blow that up a little bit. You might be able to read it from the back. Oxygen is the most abundant material in the Earth's crust. Most of the metals we have come as oxides or sulfides. Sulfur ought to be in here, down here somewhere. Silicon dioxide. Dirt, okay? Aluminum, more abundant than iron, but iron is 5% of the crust. That's pretty abundant. It's not too hard to find iron ore. By the way, on recycling, people are very proud of the recycling rate of aluminum. Anybody know what the recycling rate of iron has been for probably 80 years? It's about 90%. But there's a very simple reason. Steel is something that in the world today we make 800 million tons a year. If you didn't recycle that, you would have some very big landfills, okay, full of steel. But steel is valuable enough to recycle. In fact, some people argue that that was one of the reasons the Japanese started World War II, because their whole industry was built before World War II on using iron ore scrap, or not iron ore scrap, but iron scrap iron from the United States. And I think there was something right before Pearl Harbor, the United States had restricted the exports of scrap iron to Japan, and some people said that was the straw that broke the Japanese back and they started the war. I'm not sure that's true necessarily, but recycling of iron is a big business. It turns out, we'll get to it, well, I'll get to it a little bit later. In the oceans, of course, H2O, okay, and then chlorine. Most of the chlorine in the world is in the ocean. And then it turns out virtually every element in the periodic table is in the ocean in some concentration. You can get gold out of the ocean, but it's more expensive than mining it out of the ground, which is why we mine it out of the ground. In the atmosphere, of course, we know what's in the atmosphere. But when you go to look at whether you want to use titanium or magnesium or some other metals, well, you find the other metals just don't have quite the abundance that steel or aluminum do. And as a result, they're relatively inexpensive. However, again, out of Ashby, we want to look at the approximate energy content. How much does it cost? It turns out that about, well, let's just say somewhere between a third and a half the cost of a piece of metal is due to the energy content. And it depends on how you account for the energy content. Mining the ore out of the ground takes energy too, but mostly just to get rid of the oxygen or the sulfur that is combined with in the ground, in the ore, refining it, smelting it, or into the metallic state. Aluminum takes 300 gigajoules per ton. Plastics doesn't take 100 gigajoules, but a ton of plastics has about 100 gigajoules of energy content. It's made from oil, basically. Okay? Copper, the problem with copper is there are not any really good deposits left anywhere in the world. Back years ago in the Congo, they had 6% copper ores. Very nice. The largest copper mine in the world, anybody know where it is? Anyone from Utah? Anyone from Salt Lake City? Sometimes as you fly into the Salt Lake Airport, they'll take you over the Bingham Mine, okay? And the Bingham Mine is the world's largest open pit mine. It kind of goes between a bunch of mountains, and it's just a big valley there. And it's the largest open pit mine in the world. And the copper ore there, and the Bingham Mine's been operating for like 80 years or something, 0.5% copper. So to get 1 ton of copper, you got to mine 4,000 tons of ore, or 400 tons of ore. Okay, you start figuring out the energy content just to dig that out of the ground. So the problem is copper is just not found in really strong concentrations. And then a lot of copper ores are sulfide ores, and sulfur, you get sulfur dioxide. Okay, zinc. Okay, so this is the energy content, and that's iron is, steel is down here at 50, 1/6 the amount of aluminum. And people used to predict, oh, aluminum's going to get cheaper. There's about a 4 to 5-fold cost difference between steel and aluminum. And people said, oh, well, if you just use more aluminum, the cost will come down. No, it won't. Not when the fundamental cost is the energy content. I'm sorry, that argument doesn't work. Okay? They might have taught you that in business school, but if you actually look at the physics, or the chemistry in this case. Now, if you know what the relative price based on energy is, you also have to think about what the value of a pound saved is in some industry. And the value of a pound saved, and this is actually in that article from the materials research, the little appendix, 4-page appendix that I handed out. Although it's expanded a little bit. It's kind of an old slide. Over the life of the vehicle, the value of a pound saved is, an automobile is $2 a pound. That's at $2 a gallon gasoline. Maybe it's $3 a pound now. But basically, if you take a pound out of an automobile, over 100,000 mile life of the vehicle, you can calculate it out. So many miles per gallon. You're going to save about $2 a pound. In an aircraft, commercial aircraft, it's about $200 a pound. Now I remember when LFM first started in 1989, I had some students working at Boeing, or I didn't have them, they weren't working with me, I wasn't the thesis advisor, but we had some students working at Boeing on composites. Because for the 777, they wanted to introduce more composites. And Boeing had a figure, an internal proprietary figure that somehow made it into these students' theses. So it's not really proprietary anymore. $188 a pound was Boeing's number, was the value of a pound saved. And that's over about 100,000 hour life. An automobile, we're talking 100,000 mile life, and a commercial aircraft, you're talking roughly 100,000 hour life. All those commercial jets that are parked in Arizona, that big air base, they're about 100,000 hours. So once they got 100,000 hours on them, it starts costing more to repair them and maintain them than it's worth. So they kind of park them. So we're talking different types of lifetimes, but the value saved is about $200. Now, that's why at some place like US Airways, they have a vice president who has to decide how many coffee pots, how many magazines are carried on that airplane. Because at $200 a pound, putting an extra couple of coffee pots on that can cost you hundreds of dollars. More than the cost of the coffee pot, obviously. Okay? You're just adding weight that you have to. Now, the interesting thing, this number, if you go back to the early days of the space shuttle, they were trying, the original goal of the space shuttle was drop the cost of getting a pound of payload into space. Now, this is a one-time use type of thing, right? But it was running in the mid-70s at about $20,000 a pound, and the space shuttle was supposed to lower the cost to only $10,000 a pound. Okay? So you've heard people talking about colonizing Mars or colonizing the moon. Yeah, $10,000 a pound, great. Yeah.
I did my senior design project on the shield for the reactor for the one to go to Mars, and the number we were using was much bigger than $20,000 a pound.
Well, that was 1975 numbers, okay? And when people start talking about the X32 Spaceplane, this guy right here, was supposed to get the price down because it was a reusable shuttle. You know, the external tanks didn't fall into the ocean and things like that. They were talking about getting down to $1,000 a pound. In fact, if you start looking at the payload in space now, and that they have fewer shuttle flights, this price they were talking about was based on like 100 shuttle flights a year. If you actually look at what the space shuttle has cost, it's more like $50,000 a pound. I don't know what number you were using.
Yeah, it's more like that.
But these were 1975 numbers. But you can see I just like the symmetry of 200, 20,000. Each one goes up by 100. And the interesting thing, if I went back here to shipping or rail transportation, guess what the number would be? 2 cents a pound. So it's the same factor of 100, approximately. That's in the article 1990. And so yeah, you can adjust them. Maybe I should adjust them and make them all, you know, price of gas has gone up. I can make that $4. This probably is around 400 now. It turns out for an Air Force jet or a Navy jet, a military jet, because of its performance and other things, the value of a pound saved is about $1,000 a pound on a military aircraft today. But in 1990, the Boeing number for a commercial jet was 188. So, you know, they're just, you know, when I'm talking about 2 orders of magnitude difference between different classes of transportation, that's what I'm talking about, right? Whether it's $4 or $2, I don't really care. In fact, in about 1995 or so, I was at a conference, and Peter Breitenbauer, a graduate of this department, who was senior VP at Alcoa, and was going around touting this mid-90s. Alcoa was working with Audi to come up with their all-aluminum vehicles and stuff. And I got up at this conference and I gave a version of this talk. And Peter got up right after me to talk about aluminum. And afterwards, he came up to me and said, "Tom, it's not $2 a pound, it's $4 a pound." Okay? Which actually went in the wrong direction for Alcoa. Alcoa's number was, in 1995, was $4 a pound. Okay? Not $2. So, you're right. I mean, you're absolutely right. Today, the space shuttle, because they don't have 100 flights a year, they're lucky if they have 15 flights a year. Okay? And if you start looking at the space shuttle budget, which has all this other stuff, and you include that in the cost of the space shuttle per pound, it's just out of sight. We would have been better off going with disposable rockets and never going to a space shuttle. But why did we go to the space shuttle? Anybody know? Space shuttle cargo bay just happened to be the same size as the Air Force's laser-based space weapon. I'm not supposed to know that, okay? But it just, by coincidence, just a funny coincidence, just happened to be the same size and same payload, okay? So we like to think of the space shuttle as, it was justified on civilian grounds for exploration of space. Bull. It was basically DOD on the side, okay? Just like most of our nuclear programs paid out of the Department of Energy, or nuclear weapons programs paid out of the Department of Energy. It's really, it was, Congress justified it on national security. And it was going to reduce costs, supposedly. Of course, it didn't reduce costs, but that's another thing. So, so here's the X32 Spaceplane. Oops, not quite as bright as I would like. Oops, too bright. Okay, so here's the X32 Spaceplane. It actually has 3 tanks, 2 hydrogen tanks and 1 oxygen tank. I always call it H2O. Okay, that's the fuel. And it turns out the oxygen tank was made out of aluminum. These 2 hydrogen tanks, to save weight, were supposed to be made out of composite. There's the composite they end up going with. There's a lot more story to that. I'll probably talk about it in one of the videotapes you'll watch. But the interesting thing about this is they couldn't, to get the weight down to make it single stage to orbit, okay? The space shuttle is 2 stages to orbit. It's got these solid rocket boosters and this great big center tank. The solid rocket boosters, they cover those steel bodies, and the big aluminum tanks, those are expendable. These fall into the ocean. But they had to get all the structural weight out of that aircraft. And so the structure itself is the tanks connected together by these ribs. And this skin is just an aerodynamic skin. It's not the structural part of it. The tanks themselves, stuck together, are the structural part of that aircraft. Okay? $1.3 billion program is part of the rapid prototyping after the first Gulf War. They had 33 months to build it, okay? From issuance of the contract to flying from Vandenberg to Redstone Arsenal and just near the Great Salt Flats or whatever. It wasn't even going to go into full orbit. It was just going to, they had to have like 10 flights go from Vandenberg to Redstone Arsenal or whatever it is, Rocky Mountain Arsenal, whatever it is. And it didn't work. And we can talk about that. Now, when we talk about if a product moves, this is another one of kind of my little things. If a product moves, automobile, aircraft, hand tools, whatever, low density is an advantage. For equal volumes, one will pay for less dense material. The relative cost based on density, if you're talking plastic, having a 100% relative cost, you get down here to steel, it'll typically cost about 15%, 1/6 the amount of plastic. You go look at values of purchasing steel at 40 or 50 cents a pound, purchasing plastic $3 a pound. I mean, this curve is not just an empirical curve. I actually put some real numbers in there for different density materials. Going from plastics, aluminum is in here at 2.7, and it's 2.5, 3 times steel. Okay, that's the shape of the curve for a structural material. So, now what does that mean? Well, just think on an automobile. I will pay more to take weight off the sprung weight on the wheels because it's moving faster than the car is going down the highway, in a sense. It's spinning around. Or I might take it out of the pistons because they're moving faster. Okay? If you think of a jet engine, I will pay a lot of money to get it off the rotating parts of that jet engine rather than the wing weight. And in fact, when we talk in the course, when I talk about friction welding, I talk a little bit about blisk technology. There's only one high volume blisk used in the world. It's a bladed disc where the blades are actually integrally cast with the disc, okay? Rather than being attached through, I mean, most of the attachment is usually through this, they call the Christmas tree structure, the root structure, okay? This cross section is a Christmas tree. That has a lot of weight to it. If you can get rid of that weight, you can take a lot of weight off that disc, which is going, depending on the engine, 20,000, 40,000 RPM. The M250 engine with its blisk, it's got a little disc about this big. It's all solid casting. And it reduces weight. A pound of weight saved on a disc for a blisk, and the Air Force had a big program to weld blades directly onto disc. Because if they could save a pound off the disc, it was worth 20 pounds in the engine, because you might have 20 discs in the engine. 20 pounds in the engine was, or 20 pounds off the disc was worth 200 pounds on the engine. 200 pounds on the engine was worth 2,000 pounds on the wings, because you had to hold these big heavy engines on the end of the wings. And 2,000 pounds of payload is worth a lot to the Air Force, okay? I mean, so for some aircraft, I don't even know what their payloads are, it depends on the aircraft, but that's a very substantial amount of your payload, either in terms of fuel range or ordnance, okay? It's a lot. So you'll pay more the faster something moves, and you can think of it as the whole vehicle, or you can think of it as the brakes on a car, okay? The sprung weight is worth more than, even though the brakes are going the same speed as the vehicle, obviously, but the sprung weight is worth more. Now, some basic laws of materials. There's a guy, Bob Sprague, who was head of materials at General Electric Aircraft Engines, and he used to say, he had some great quotes. But when you first hear about a new material, write it down, because it may be the best thing you'll ever hear about this material. So, material scientists will always tell you about their good parts, low density, low specific strength density, low specific strength, or high specific strength. What does specific mean? It means divided by density. So plastics, stronger than steel, based on specific strength. Okay, Kevlar, you've heard Kevlar is stronger than steel? On a specific basis. But on an actual basis, I'd rather, if I'm trying to be held by a very thin wire, I'd rather have a piece of piano wire than a piece of Kevlar. Okay? A piece of steel piano wire. Now, I'd just soon have 9 pieces of Kevlar, or 8 pieces of Kevlar, okay, as one piece of piano wire. But that's on an equal volume basis. Okay? So you have to be careful of these modifiers people put in there. Okay? Williams is correlated. Jim Williams replaced Bob Sprague in that job, and Jim had this statement: when you hear about the price of a new material, write it down, because it may be the lowest price you'll ever hear. Okay? Just like the space shuttle was supposed to, you know, save so much weight and reduce the cost and blah, blah, blah. It didn't quite do it. Okay? So in selecting materials, we have this interesting problem that the relative cost is a small fraction of the overall cost of things. I'll get to that in a minute. Let me actually show you. I never made a slide of this. If I take the cost of something, and I take iron or steel, and it has a relative cost of 1, and it has a density, we don't have to work too, I'll just say it has a relative density. Aluminum is about 5 times the cost and about 40% of the density. Magnesium is 10 times the cost, and it has about a quarter of the density, 43. Nickel is 50 times the cost. Now this is interesting because if you Navy guys, anybody here in the Navy subs? Some of you are, obviously. Yeah, nickel, right? Use all these things for corrosion protection, right? Only problem is it costs 50 times as much, right? But you can use it and it'll have much better corrosion resistance, right? Cobalt, 200 times. Copper, 10 times. Silver, 1,000 times, roughly. Gold, 100,000 times. And titanium, 100 to 200 times. So, why was the Navy interested in replacing steel ships, steel submarines with HY-80? Actually use HY-100 now, same composition, different heat treatment. That was actually made electric boat as a test plate. Versus titanium. This is a 2-inch thick piece of titanium. This was made at Oregon Graduate Center because of the electrostatic welding process. You can feel the difference in weight. Much lighter. Why didn't we build titanium submarines?
Lion's share of the titanium is in Russia.
Oh no, the titanium, if you remember the abundance, it's all over the world. Titanium is very high abundance. So you're right, the production capacity for titanium metal, but that was because they were on an artificial economic system, okay? It still cost them a lot of money, but they didn't have the same type of economic controls. Yes?
Some concerns about titanium over the life of the ship.
Yes, it turns out.
When you cycle it, its fracture toughness goes.
Exactly. The The Naval Research Lab had done some fracture studies, and they found there's something called a creep fatigue interaction. Okay, and we'll get into this a little bit later. And so, in 1980, when the Soviets came out with the Alpha Sub, and the U.S. found out about it, I was actually, my first research project here at MIT was on welding heavy section titanium for the U.S. Navy. I got that in 1977. It was my first research contract as a little assistant professor. And the first electroslag weld made in this country, to my knowledge, was made right down there in that laboratory right across from my office. And then, this was about 1981, when I was at a conference down at David Taylor at Annapolis, a titanium conference, and I was talking about heavy section. I was talking about welding 1 inch thick. The Navy was coming in talking about 1, 2, and 4 inch thick materials. And industry came in. The thickest material they talked about was 3/8 of an inch thick titanium. It was all aerospace stuff. Most people were talking 1/8 of an inch was heavy section titanium to them. Okay? So the only people working in the United States were MIT and the Naval David Taylor working on real heavy section. The Soviets had had a huge program for many years, and I've been reading the Soviet stuff, and I'm sitting there at David Taylor in this conference. I'm sitting there we're trying to figure out how did the Soviets build this titanium submarine in this conference. And I thought, I was thinking back to the literature. I remember there was all kinds of Soviet literature in the 60s about electroslag welding of titanium, but the Soviets did all this work on electroslag welding of steel and other things. The Patton Institute in Kiev was built on electroslag technology, okay? But then I thought, you know, about 1972, all those papers stopped in the open literature. And I got people in the hallway at the coffee break. I said, they used electroslag, okay? And so we came back and we set up and we made an electroslag weld about a month later. And sure enough, it was a lousy weld. Okay, but we proved that, yeah, you can do it. There were a few, then they basically, they moved it to Oregon Graduate Center because they would do classified work at Oregon Graduate Center. And that was given to me a few years later, that little sample. And I can tell you, the Soviets did use, in fact, later in this 12-minute thing, we'll probably talk a little bit about welding of titanium heavy section. And electroslag was one of the technologies they used to build the Alpha Sub. Okay, I figured it out by just kind of thinking about what I saw in the literature over the previous 20 years before 1980. Okay, but the real reason the U.S. well, two reasons. One was cost. They could not figure out how would you rather have 10 steel submarines or 1 titanium sub? Okay, that was kind of the trade-off at NAVC. Okay, they could have built one, but there was also this creep fatigue interaction that you talked about. Okay.
Besides, it's cheaper to build a torpedo that can shoot a submarine that goes deeper than it is to build.
Right, and I remember in 1980 when that Alpha Sub came out, people were saying, well, the Alpha Sub can go faster underwater than our destroyers can go on the surface. And another person said, and they can dive deeper than the collapse depth of our depth charges. And one guy says, it depends on the type of depth charge. Some depth charges you only have to get within a few miles. Right?
Yeah, but your survivability, your personal survivability goes away.
Well, you know, if you're in that kind of
exactly
conflict, it probably does anyway. Right? Okay, so in any case, there's lots of different ways you can play the war games, right? We don't have to get into that, but cost was a big issue. Creep fatigue interaction was a big issue. And I guess I probably shouldn't get into some other things on that. Another thing I like to look at, here's my factor of 100 here. Between copper, silver, and gold, 10, 100, 100,000. Okay? The precious metals or semi-precious metals or whatever you want to call them, there's about a factor of 100 difference. And this has to do with the relative abundance and how many tons of ore you have to move to get a ton of product. Okay? These primarily have to do with the energy cost of extraction, which includes how many tons of ore, you know, the relative abundance and things like that, okay, as well. But not just that, the total energy cost. Let's only need that. Now, let's look at the overall use of structural materials. This you have in your handout, that little paper that the Appendix C that I wrote. But this has been redrawn by the National Research Council, but this is the original drawing from 1962, an internal General Electric report written by a guy named Jack Westbrook, who's an MIT grad. And he was doing a study for General Electric on the pounds per year of a material's use versus the dollars per pound. And this is 1962 dollars, okay? But nonetheless, the most commonly used material was the same one we used 10,000 years ago, and that's stone, at 10 to the 12th pounds per year. We use gravel more than anything else. But we tend not to ship it around the world because it's only worth 1/10 of a cent a pound, okay, in 1962 dollars. Brick is up there, cement. Cement today, there's been a tremendous growth. Cement, we use 1.6 billion tons a year is what we produce in the world. Steel is half of that. It's 800 million tons. Cement is 1.6 billion tons. On a tonnage basis, and on a volume basis, like 4 times the volume. And that's because it's a cheaper material if you're going to build bridges and buildings in the third world. As the third world, the growth rate of cement over the last 10 to 15 years has far outstripped the growth rate of steel, because it's going into third world countries where they need a cheap building material. Now, it's not necessarily the best building material for lightweight and other things, but it's cheap, okay? Now, one of the problems with cement is you can't afford to ship it very far. My father worked in the cement business, and it turns out he went to work for a company. Eventually I ended up graduating from high school in Virginia Beach, because he worked for a company in Norfolk, and the cement kiln was in Ravenna, New York, on the Hudson River, and they could use barges, cheapest form of transportation, right, to move the cement all the way up and down the East Coast. And so Norfolk and Savannah, different places, they supplied the whole East Coast of the United States out of one cement plant. Before that, you had to have a cement plant, like, couldn't be more than 1 state away, because you couldn't afford to truck that cheap material very far. So it's all kind of production and transportation.
That's kind of interesting. They just did a road reconstruction in Norfolk, and they basically moved the plant, ripped up the old cement, made a big pile, recycled it right there on site, and relayed it.
Because recycling of cement is getting to be a big issue. You can't just kind of keep landfilling 1.6 billion tons a year. One of the biggest problems we have, if you want to figure out a good business, if you got a way to figure out how to recycle 1 billion tons of cement a year, that would be a good business if you can figure out how to do it profitably. Because we're using more cement in the world, more concrete, and we got to figure out how to reuse it. So as you said, they're just using it, turning it into gravel.
Yeah, they just ripped it up, turned it into gravel, and processed it.
Wood, there's carbon steel is up here, alloy steel, so you can kind of add the steels together if you want. Zinc, nickel, this plot is in your thing. Tantalum, diamond's out here. Diamond is a structural material. We use it as an abrasive, okay? So it's a structural material, okay? But it's the most expensive one. These lines here are ISO market lines in 1962. I actually had a student, I wanted to get an undergraduate to redo this, around 2000. And it takes a lot of time to generate the usage of each material as a structural material in the world, and the cost and everything. But nonetheless, these are ISO market lines. And the interesting thing here is the slope of use is steeper than the constant size of the volume. What that tells you is that over the long run, not the short run, but over the long run, if I can drop the cost of a structural material by a factor of 2, I should increase its use by a factor of 4, which means I should double the size of the industry if I can take half the cost out of the structural material. Now, it's not that easy, because the high volume structural materials, I got a lot of competition. There are people out there making 800 million tons of steel a year. And until recently, until the metals market blew apart, they were losing money in that industry. We'll talk about that probably tomorrow. But let me just finish up with this little thought, that over the life of a product, or not over the life of a product, but in producing something, the materials cost is a relatively small cost of the overall cost of production. Okay? For automobiles and aircraft, the cost of materials cost about 10% of the cost of the car or the aircraft. A pipeline, like a gas pipeline or oil pipeline, has the highest materials cost of anything I know. About 1/3 of the cost is the cost of buying the pipe, steel pipe. Laying it is only, and inspecting it and stuff is only about 2/3 of the cost. Semiconductors, functional materials, or very high value-added materials like spacecraft, the actual cost of buying the material is only 1% of the overall cost. The real cost is making those silly things. But when you start thinking about this, and I started telling you, remember $2 a pound saved over the life of the vehicle? Well, the materials cost can only be 20 cents a pound in an automobile. And the problem was, aluminum cost a lot more than 20 cents a pound. Steel, back 15 years ago, was costing about 20 cents a pound. So you could make automobiles out of steel. But you couldn't afford to make them out of aluminum unless it was a $40,000 Audi. And that's what I used to say in 1995. I said, hey, any fool can make a $40,000 sedan out of aluminum, but who can make a $15,000 sedan out of aluminum? Nobody. Okay? Turns out the basic steel structure of the car is worth about $500 worth of steel. But in aluminum, it's like $2,500. So an extra $2,000 on the cost of a $15,000 car, that's a hit. Okay? But on a $40,000 Audi, no big deal. Someone's paying $40,000 for an Audi, they're not price sensitive. If it costs $42,000 or $38,000, you know, it comes out in the wash, right? You can sell them the pizzazz for more than $2,000, right? Okay, so see you tomorrow, and we'll find